Hello everyone and welcome back to our channel mootechie. We're continuing with Unit 5 on mixing and agitation, and this is Class 3. Today we're going to focus on the design principles and the theory behind calculating the power needed for mixing. We'll start by looking at the standard design proportions for a turbine agitator. For a well-designed system, we use specific ratios. The ratio of the impeller diameter, dA, to the tank diameter dt should be 1/3. The ratio of the liquid height, h, to the tank diameter, dt should be 1. The ratio of the baffle length, j, to the tank diameter, dt is 1/12. The height of the impeller from the tank bottom, e, relative to the tank diameter, dt, is also 1/3. For the impeller itself, the blade width, w, relative to the impeller diameter, dA, is 1. The baffle length, j, relative to the impeller diameter, dA, is 1/4. Next, let's discuss the theory of liquid mixing and power requirements. The power needed by a mixer depends on the type, amount and viscosity of the food, as well as the position, type, speed and size of the impeller. We use special dimensionless numbers to describe the flow. The Reynolds number, Re, tells us about the flow pattern. The Froude number, Fr, relates to vortex formation. The power number, Po, relates to power consumption. The Reynolds number, Re, is calculated as d squared times n times the density ρm divided by the viscosity μm. The Froude number, Fr, is calculated as d times n squared divided by gravity g. The power number, Po, is calculated as the power P divided by density ρm times n cubed times d to the power 5. Here, d is the agitator diameter in meters, n is the speed in revolutions per second, P is power in watts, ρm is mixture density, and μm is mixture viscosity. These numbers are related by the equation power number Po equals a constant k times the Reynolds number Re to the power n times the Froude number Fr to the power m. The values of k, n, and m are found by experiment for each agitator design. The Froude number is mainly important if a vortex forms in an unbaffled tank, so it's often left out of the equation for baffled tanks. Another important concept is the flow number. The flow rate, Q, from an impeller is proportional to its speed, n, and the cube of its diameter, dA cubed. The flow number, nq, is defined as the flow rate, Q, divided by n times dA cubed. This number is constant for each impeller type. For a standard flat blade turbine in a baffled tank, nq is about 1.3. For a marine propeller, nq is about 0.5. For flat blade turbines, the total flow in the tank Qt can be estimated as 0.92 times n times dA cubed times the ratio of tank diameter to impeller diameter dt divided by dA. This equation is best used when the dt divided by dA ratio is between 2 and 4. Now for power consumption in turbulent flow, the power P can be estimated as the flow rate Q multiplied by the kinetic energy per unit volume. The flow rate Q equals n times dA cubed times the flow number nq. The kinetic energy per unit volume equals the density ρ times the velocity v2 squared divided by 2 times gc. The velocity v2 is the actual fluid velocity at the impeller tip. By substituting and rearranging these equations, we arrive at a dimensionless group called the power number Po. The power number is defined as P times gc divided by n cubed times dA to the 5th power times the density ρ. The significance of these dimensionless groups is key. The Reynolds number comes from the impeller size and speed. The power number is like a friction factor. The Froude number compares flow forces to gravity. Engineers use a standard plot, a curve showing how the power number changes with the Reynolds number for different impellers to easily find the power needed for their specific mixing setup. Thank you for joining this session on agitator design and power calculations. Understanding these concepts is essential for selecting and operating efficient mixing equipment in the dairy industry.